So before I get started, I just want to take a minute to mention how amazing it is that there's an entire room filled with people here for WebAssembly. I've been waiting for a day like this for years, so this is good stuff. So I don't want to talk too much about myself. I just want to put this up here to let you know that I have a very noticeable bias. I am a back-end person. UIs, web browsers, graphical interfaces, those all occupy the same space in my mind as mythological creatures. They don't exist. They might somewhere, but not for me. I access the web through a Bastion host and curl. So everything I'm going to talk about here is obviously back-end oriented. Browsers aren't real. So why should we care about WebAssembly in the context of the fictional concept of browsers? Again, I've heard about this browser thing, and WebAssembly has a bunch of benefits for the browser. Things like speed, small footprint, security, developer productivity, and things like being able to deploy and rapidly and continuous deployment. All of these things are things that benefit us in the cloud as well. We want our cloud workloads to be fast. We want them to be small. We want them to be secure for a number of different reasons. We want to be able to verify that our workloads haven't been tampered with. We want to be able to prove provenance, chain of ownership, things like that. The memory sandbox and memory isolation works for us in the cloud. And we also want developer productivity and continuous deployment. So WebAssembly itself is small. I'll demonstrate a microservice that's running, and its compiled WebAssembly file is 2 megs without optimization. Most of the work we do in the host runtime, not in the WASM file. It may or may not be a coincidence that I've lost 51 pounds since I started learning WebAssembly. True story. Thank you, sir. Oh, see, now you guys are just going to completely mess up my rhythm. But no, seriously, the applause is great. Thanks. WebAssembly is secure. So I don't know if anybody has heard about buffer overrun type of security exploits. Things like that are physically impossible inside a WebAssembly module. WebAssembly, the specification allows us to have custom sections. So we can put metadata directly inside a WebAssembly file, things like hashes and signatures. The host decides what the module can and can't do. And again, we have the isolated memory sandbox that can't leak or allow exfiltration of data that we don't want. Kind of a caveat here is that the WebAssembly format you've already seen is a well-known standard, so it can be easily disassembled. So obviously, despite all of the security benefits, don't put trade secrets in your compiled WebAssembly modules. Same reason we don't do that in JavaScript, or we try not to. WebAssembly is portable. We've seen examples of this running in the browser. We've seen examples of WebAssembly running on IoT devices. It's OS agnostic, platform agnostic. My personal agenda is that it doesn't require containers. And of course, it's only as portable as we make it. So it's portable now. The spec calls for it to be portable, but as a community, we can easily screw that up. So we need to make sure that, as we go forward, we don't do anything that gets in the way of WebAssembly's portability benefits. WebAssembly is, in theory, polyglot. We have languages that we can use to host as host runtimes for WebAssembly, and we can write WebAssembly modules in nearly any language. Rust, Go, Quick show of hands, does anybody use the language called Zig? Yes, excellent. Assembly script, we saw a bunch of really amazing stuff there. I put an asterisk next to Go because Go's current implementation assumes the existence of a JavaScript runtime, which really bothers me because, like I said, front ends don't exist. So, like I said, there's a number of different ways we can host WebAssembly outside the browser, and that's done through host runtime. At the lowest level, you have interpreters and compilers. So you've got runtimes that will interpret the WebAssembly instructions, and you have some that will just in time convert the WebAssembly into native code. And you saw earlier that there are ways to do a combination of both of those for various different optimizations. We've got WASMtime, which is a host runtime from the Bytecode Alliance, WASMer. You saw a demo of WASM 3, and you also saw the link to the list of awesome WASM runtimes. At the building on top of, hold on a second here. Yeah, building on top of the low-level runtimes, we've built some open source projects. The first one is WAPC, or WebAssembly Procedure Calls. And it is a layer on top of the low-level runtime that allows us to pass arbitrary payloads back and forth between the host runtime and WebAssembly. And this gets us around the limitation that WebAssembly only supports numeric arguments. And having to deal with that complexity on our own is difficult and pretty high friction. And what we're trying to do is make things easier for developers to use WebAssembly. Kind of a subtle distinction, but important to me, is that in this contract for passing information back and forth between WebAssembly and the runtime host, neither side is aware of the other side's memory allocation pattern. So things like interface types and some of the other things like mscripton and if you're familiar with WASM bindgen for Rust, they all work by allowing the host to allocate memory inside the guest, or the guest to allocate memory inside the host, which means that that interaction is stateful. And if it drops, then you lose those pointers. And WAPC is designed to be stateless, so there is no memory allocation. I can go into detail on the contract later, but. And then there's also a set of tools around signing WebAssembly modules with JSON Web Tokens and embedding those directly in the module, and I'll show some of that too. And above that runtime is yet another layer, and this one is called WASC, or WebAssembly Secure Capabilities Connector. And what we've done with this one is essentially taken the concept of a WebAssembly module and applied it to the concept of actor systems. And so we want developers to build web services or microservices and functions as pure business logic compiled into a WebAssembly module that is secure and signed and then dynamically bound to capabilities. So take away all the boilerplate that we normally spend with our non-functional requirements like message brokers, HTTP, key value stores, all that stuff, and dynamically bind it. So we can leverage the portability and small size of the WebAssembly modules. And again, I'll get into some demos of that soon. I just want to go through the list here. Right now, the host and guest parts are all written in Rust. Once Go becomes more compliant with the WebAssembly spec, we'll have a Go SDK for that as well. So let's take a look at the WebAssembly ecosystem, again, out of the browser. So one of my favorite quotes is, "If I have seen further, it is by standing on the shoulders of giants." And one thing that we have to deal with as a young community is that there just isn't that much out there. There isn't that much tooling, and if there is, it's not all that mature. We're missing things like documentation, training, things like that. And so in order to stand on the shoulders of giants, one thing that we often have to do is build our own shoulders. So if there isn't tooling, we have to build it in order to make these products work. So the things that I'm going to talk about are things like out-of-browser runtimes and tooling, but we also, as a community, need to work on things like education, documentation, developer experience, things like that. So the most important part of this presentation is demos. I'm going to take a walk through the different tiers that I talked about. So the first one is the core WebAssembly runtime, and then we'll talk about WAPC and how to do essentially remote procedure calls with WebAssembly, and then I'll show a demo of running WebAssembly modules as services in the cloud. So, so that everybody can see that. Again, like I said, this is my UI. So the first thing I want to do is quick show of hands. Has anybody seen or done programming with the low-level WebAssembly text format? That is awesome. That is the first room where more than one hand has gone up. It makes me, yeah, it's all downhill from here. So we compile one of these into a WASM file, and we can use a number of different runtimes to invoke or to exercise this WebAssembly module. Let's see if I can remember the syntax offhand. Since math is not my specialty, we'll go with 2 and 2, and we get 4. So, like I said, this is a low level, and kind of the reason why I wanted to cover this is because this is what WebAssembly Core gives us. This is what the spec gives us, and this is what the basic tooling gives us. Everything above this is something that we have either had to write ourselves or rely on someone else to write. So I've got a couple of demos here for WAPC. And like I said, this is a contract between the host runtime and a WebAssembly module that allows the host runtime to make calls into the WebAssembly module and the WebAssembly module to make calls to the host runtime. So that bidirectional contract, and again, it's without explicit memory allocation. That's not right. Examples. So in here, we're going to load our WebAssembly file, and we'll use the WAPC library to create a WAPC host. And we have a call function which invokes an operation with an arbitrary blob of bytes, and so in this case I'm just sending it a string. And again, this is important because WebAssembly doesn't support string parameters, so if you use things like interface types, then it will dynamically convert strings, but again, that uses the explicit knowledge of allocation that I wanted to avoid here. So I think there's definitely situations where you might want both, but having those long-running pointers is something that just sort of creeps me out when running in the cloud. And so we have call, and then we have a callback, which allows the WebAssembly module to invoke Rust code or any code on the host. So we'll see if I can. I'm sorry about the environment variable. I forgot to set that earlier. So it did as we expected it to. Thank God. I'm so glad my demos worked. So what happened was the host made a call into the WebAssembly module, and in response, the WebAssembly module made a call to the host, and we got all that output here. And so, again, this is one of those building blocks where now that we have the ability to send and receive opaque binary blobs, the next step is to assign some meaning to those binary blobs and then provide some sort of framework that we can use to build cloud-native services in WebAssembly. So that's what I'm going to show next. So running in this window, what I have is a WASC, WebAssembly Secure Capabilities Connector. That's the last time I'm going to say that. That host is running, and if you built services in the cloud before, this should look pretty familiar. It's just a bunch of UI. So this service is running, and what is, no, I don't want to close. What's running in there is a WebAssembly module called KV Counter, and that module receives a request, a GET request over HTTP, increments a counter atomically stored in a key value store, and then returns that value in a JSON payload. And that type of activity sounds simple and easy to do, but of course, once we get down into the details, we have all these non-functional requirements that we normally have to deal with. The HTTP server, talking to the key value store, all these things that are boilerplate that have nothing to do with our business logic. And my hypothesis is that we can use WebAssembly to get rid of all that boilerplate. So I can. I'm just going to try and find the example code here real quick. There it is. So this is the entire source code for the KV counter. We receive a message. One of them is handle request, and the other one is a health check. We do the health check because clouds need health checks. And the code to increment the counter just calls an atomic add operation, and then we return, essentially, we return a protobuf message that is then converted into a web result. And what's important here is that none of these capabilities, the key value store, the HTTP server, the health checking, none of those are tightly coupled. Those are all dynamically bound to the WebAssembly module at runtime. So that's the code that's running, and so I can exercise that code from, I don't know what this thing is. It's some sort of tool. So here is the essentially a summary version of the code that we're writing. So I hit the button and then execute it, and if we look down here in the real UI, you can see that we handled the web request, sent the request into the WebAssembly module, got an answer, converted it to a web result, and again, the WebAssembly module is blissfully unaware what the HTTP provider is and what the key value store provider is. And ordinarily, that would be decent enough, and we would go and start building our services with this. But because we're using WebAssembly and because it's portable, we have a number of things that we can do inside WebAssembly, and this is sort of the point of the talk, that we cannot do in containers. So the first thing I'm going to do is live swap the WebAssembly module that's running with another version without having to provision new resources. And so in other words, we get zero downtime deployment without having to provision new resources. So now I have the second version of my WebAssembly module that was running, and I don't know if you noticed the slight delay. We didn't drop a request, we just blocked and paused long enough to allow the swap to happen. And the reason why that swap takes about a second is because I'm in debug mode. Obviously this would be faster in production. So the other point is that the key value store is also dynamically bound to this module. So the next thing here is I can remove the key value store from the host runtime, and now I get an error. But what happens here is that the host is up enough to be able to give me a decent error message so that my Kubernetes cluster knows that I've failed a health check, or if I have downstream circuit breakers, those can all trigger with the appropriate response rather than having catastrophic failure. And so what I've just done is swapped the Redis counter, or the Redis key value store, with an in-memory one. So the next time I make a request, my value has gone back down to 1. So without taking the host down, I can perform a live update of my business logic, and I can perform a live swap of any of my capability providers. And the reason why all of that dynamic ability is possible at runtime is because of WebAssembly and the fact that I'm not using Docker. I mean, I have nothing against Docker. I just think that there are some and I'll harp on this point a bunch, but there are limitations that we can leverage in WebAssembly, and if we embrace those limitations and constraints, then we get some of these features. One of the other things I wanted to show was the security aspect of this. So what you didn't see is I'm doing some security validation on the WebAssembly module itself. So this tool is reading the embedded security token inside that WebAssembly module. And you can see the public key of the issuer, the public key of the WebAssembly module itself, other token information like when it expires, when it can be used, the versioning information, and most importantly, the list of capabilities that this module is able to use. So you can see that it's been provisioned to use the key value store and the HTTP server. But if I even attempted to load this module at runtime, and that module wanted to use the web server, but it wasn't granted that permission, it simply wouldn't be able to do so. And so, today with Docker, we go through an awful lot of hoops in the environment itself to prevent our Docker images from doing things that we don't want them to do. But by embedding the security information inside these modules, we can have that information go with our immutable deployment artifact and not be dependent on the environment that it's running in. So I went through and showed the 3 different levels. So we have the all natural free range WebAssembly, which is the core spec. So sending in numbers and getting numbers back. Built on top of that, we have WebAssembly procedure calls. And so if that's the level of abstraction that you want to use, then you can use just that open source project. And there's already a couple of people that are using it at that level, and they don't want to use the higher level. But then if you want to have your development teams be able to build secure, verifiable services and functions and deploy them in the cloud, then we have WebAssembly Secure Capabilities Connector. So the basic thing that I want to make sure, if there was one thing that you remembered from this presentation, other than the fact that browsers don't exist, is WebAssembly is the future of distributed computing. That's not, obviously that's not opinion, that's objective fact. I would like for people to get involved. So like I said, this is the first time I've ever seen a room filled with people that actually care about WebAssembly. So we should take advantage of that. And so you can take a look at Bytecode Alliance and figure out if there's a way you can contribute there. All of the stuff that I demoed is available on GitHub, WebAssembly procedure calls, WASC, and basically I just want people to start building amazing things outside the browser with WebAssembly. That's all I had.